Swayam Prabha. Digital India. Educated India.
Which is entitled Dispersed Multiphase Flows. Myself, Sri Krishna from the Department of Mechanical Engineering, IIT Madras. So, before we begin the course formally and I discuss the scope and the syllabus of the course, let me first introduce you to the multiphase flows and give you a basic background on what is multiphase flow, what is dispersed multiphase flow, okay, that we are going to study, and what are the applications and challenges involved in understanding such kind of flows. If you consider this term multiphase flows, so there are two terms here, multiphase and flows. What is meant by multiphase? Multiphase means presence of more than one phases. That is, we have, if we ignore the plasma state of matter, we have three phases: solid, liquid and gaseous phases. So, the flow in which we have the presence of more than one phase is multiphase. Now, second term is flows. This means that we must have a system which is in flowing stage. So, flowing stage means what? So, let us say you consider flow of water in porous media. Let us say you put some water in sand, then what happens? The sand, the water sinks into the sand, but it actually flows through the sand. So, that is an example of flow through porous media. But can we call that as multiphase flow even if there we are dealing with two phases, that is the solid phase, the porous medium, and the liquid phase, the water, but still that is not multiphase flows because we need this system to be in flowing stage. Okay. So, another thing that also needs attention here is the distinction between phase and component. Are multiphase flows multi-component flows? Now, what is the difference? So, here component refers to the constituents in a phase. For example, air. We know that air is a mixture of gases. Okay. So, nitrogen, oxygen, hydrogen and many other gases. So, these are components, but air, that does not mean that air is multiphase. Air is a single phase flow but multi-component, it has multi-component. So, now we have different possibilities. So, yeah, but many times we consider air as a single component also. Okay. So, we have single component, multi-component flows, we have single phase and multi-phase flows. Now, can you give an example of the flow which is single phase, single component, water, or say flow of any gas? Okay. Say hydrogen is flowing through, say, your burner, then that is an example of single phase, single component flow. Single phase, multi-component flow we have already discussed, or let us say you have a mixture of methane and hydrogen, or let us say you have exhaust gases from an engine. Okay. So, this is single phase, multi-component. What is an example of multi-phase, single component flows? Steam water flow. Okay. So, we have water vapor in water, okay, or refrigerant flows in a refrigerator. So, there in an evaporator of a refrigerator. So, that is multi-phase, single component. So, similarly we can have multi-phase, multi-component flows. For example, a spray, let us say the spray coming out of a let us say deodorant. So, when you press the plunger, so you have millions of small droplets which are injected and which are dispersed in air. So, you have a liquid which is dispersing in air. Okay, so, it is multi-phase also multi-component. Coal water slurry, coal and water, different phase as well as the components are different. Okay. So, like this we have different scenarios possible. Okay. Now, what are the main differences between single phase flows and multi-phase flows? Now, first single phase flows, we know that the governing equations are well established. What are the governing equations for single phase flows? Mass, momentum, energy equation. Okay. For gases you can say ideal gas also. So, these are all the equations are well known, they are well established. Okay. The thermophysical properties are also available, properties of the fluid are available. What are the main concerns? Are there anything which are yet unknown? The answer is turbulence. So, it is, we should not say it is unknown, but it is rather partly known. Okay. So, turbulence and its influence on mass, momentum and energy transfer. So, this remains as one of the classical problem which is unsolved. We know about this. Okay. Now, coming to multi-phase flows. In case of multi-phase flows, the correct formulation of the governing equations are still subject to debate. So, why is this so? We will see this more detail when we discuss the transport equations for the multi-phase flows later. But the main reason behind this is basically due to the presence of the dispersed phase. So, we have now, we need to have equations, transport equations for the dispersed phase and the carrier phase. Okay. And they are also interrelated, and that brings in the complexity. Okay. And the data on properties are incomplete, empirical, or it requires separate estimation techniques. We will see this also. And the models, the state of the art for the multi-phase flow models are still at a primitive stage. So, obviously turbulence further complicates this scenario. So, when turbulence is not well understood for single phase flow itself, so when we have multi-phase flow, so obviously it will bring in complexity. However, turbulence is not the only reason which brings in the complexity. Okay. So, why we have this complexity? Mainly because of the interfacial interactions and coupling between the phases. So, due to mass, momentum and energy exchange between the two phases. So, that is what brings in complexity. Okay. So, now we understand what is multi-phase flows. Okay. So, we can categorize multi-phase flows into two categories as you can see here. One is dispersed flows and the other one is separated flows. So, now what are those? So, in case of separated flows, you see that here we have the two phases, still we have two phases, but both phases are continuous. What is meant by continuous? This means that you can move from one point to another point in one phase without interacting with the other phase. Okay. So, for example, in the liquid you can move from one point to the other point and you do not have to bother about the gas, or you do not have to, no I should, so basically the gas influences the liquid of course, but we do not have to pass through the gas. Okay. So, can you think of any example of this kind of separated flows? For example, you have air flow over water in a pond. So, you see large waves which are generated because of the interaction between the air and the water. Okay. Then we have dispersed flows. Dispersed flow means as I have already mentioned, so there are two parts to it. One is dispersed phase, one is continuous phase. Okay. So, here in this example you can see you have a liquid which is shown in blue color and you have gas bubbles shown in white color. Okay. So, in this case you can't pass from one particle to another particle without interacting with the continuous phase. Okay. So, this is a typical characteristic of a dispersed multiphase flows. Okay. So, basically you can say that the dispersed phase is embedded in the continuous phase. Okay. And we need to understand the behavior of both the dispersed phase and the continuous phase at the same time. On the other hand, in case of separated flows, yes, here also we need to understand the two phases, but they interact only at the interface. So, that is the main difference. Okay. So, now, but we may not always categorize the flows as dispersed flow or separated flows. For example, in case of slug flows you see here. So, here we have large gas bubbles, okay, and here also the interfacial interactions becomes important, and we may not treat these large bubbles as a single particles, okay, as in the case of the dispersed flow. Okay. So, we can have even more complex scenarios. So, in this case where you see that we have the vapor bubbles in liquid, but somehow the liquid droplets are also entered in the vapor. Okay. So, this kind of scenario is also possible. Another interesting example is atomization itself in general. So, here I am showing an example from an air blast atomizer. So, basically in this case you have a liquid jet which is injected at the center of the atomizer, but around this there is very high speed airflow that you obviously you cannot see. But here you see this is what happens close to the injector exit. But if you are far downstream, you see the flow of droplets. So, now this part we can argue that this refers to dispersed flow, but this one, is it dispersed flow or separated flow? So, this is more close to separated flows, because here you see due to interaction between the liquid and the air, the instabilities develop at the interface and the instabilities grow and they break the liquid jet into ligaments and droplets. Okay. So, the point here is in the same device you encounter the dispersed flow in some location and separated flow in some other location. So, accordingly the analysis has to be different. Okay. This is also another example where you can see the breakup of a droplet. So, due to high speed airflow. So, here you have a high speed airflow coming from an injector from left to right, and we have a droplet which is introduced into the flow, and the droplet breaks into multiple smaller droplets. So, what do you think, how do you analyze this? So, first part, till the breakup process starts. So, till the breakup process starts, so you have injected the droplet, okay, and it deforms. As soon as it interacts with the air, it deforms and then breakup starts. So, till that point, it may be possible to analyze that as dispersed multiphase flow. But once it starts to break, then it is, so you have to consider the instabilities which cause this breakup. Okay. But once the breakup process is over and you have all small droplets generated which don't further break up, that part can again be considered using the dispersed multiphase flow analysis. So, you see, so this kind of scenario is also possible. Now, we will look at various categories of dispersed multiphase flows, different possibilities. So, we know that the dispersed phase can be solid, liquid or gaseous phase, the dispersed phase. But the continuous phase can be only liquid or gas. Okay. So, now we will see different combinations. So, liquid particles in liquid flows. Any example? Liquid particles in liquid flows. Let us say you put some oil in water, okay, and you stir it, okay, then the flow may mimic, it depends on how well you are agitating, okay, and here we are referring to emulsions. So, liquid particles in liquid flows. Then liquid particles in gaseous flows. Any example? Liquid particles in gaseous flows. Humidity, no. So, when you talk about humidity, you are referring to the water vapor present in air. You do not have different phases. Any example? Rain, rain formation. Okay. Okay. Then solid in liquid, solid particles in liquid. So, we have many different types of slurries, okay, which are, we'll look at all this in detail later. So, then we have solid in gas, solid particles in gas. Any example? Dusty flow, dusty air, good, yes. Then gas in liquid. Is it possible that we have gaseous particles in liquid? Huh? Bubbles, yes, good, yeah. So, bubbles is a very good example. We can have also other complex scenarios where we can have liquid plus solid particles in gas, or solid plus gaseous particles in liquid. Okay, we will see this. So, now I will take you through various examples where we encounter multiphase flows in these different scenarios. So, based on our discussion, we see that these are the different types of dispersed multiphase flows that we can encounter, and they have wide range of applications ranging from energy propulsion systems to manufacturing, processing, means process industries, transport systems, nature and environment, medical and agricultural applications. So, let us see one by one. Okay, so, in this slide I show the examples of liquid particles in gaseous flows. Okay. One common example is a spray. So, what is a spray? So, by spray we mean disintegration of a bulk liquid to multiple small droplets. Why? The main purpose here is to achieve very high surface area to volume ratio. So, for a given volume of liquid, we can significantly enhance the available surface area if we distribute the liquid to small droplets. Okay. So, the sprays themselves have wide range of applications. Okay. So, as you can see here, this is a spray for IC engine, that is internal combustion engines. This is a spray from a model gas turbine injector. This is a spray from a model injector for rocket engines, and this is an industrial spray. This is known as air assist spray. This is used in various industries, industrial burners. And then we have application in transport, in defense space, fire control. Sprays are used for fire control also, we know that. Then spray drying. So, spray drying is an application, so where you generate powders, for example, detergent powders or milk powders, okay, by spraying into a hot air, okay, and then you do this drying of the particles, of the droplets. And then we have spray cooling applications, as you can see here in power plants. Then spray coating is also very important. Then spray pyrolysis. So, spray pyrolysis is, for example, we can use that to synthesize nanoparticles, okay. And emission control, though I haven't shown here, this is also very important in all diesel engines, mainly medium duty and large duty vehicles. To control the emission, they inject urea water solution in the exhaust duct, because this when we inject the urea water solution, it generates ammonia, and ammonia reduces NOx to nitrogen in the presence of a catalyst. This is known as selective catalytic reduction. And then we have medical applications also, as you can see here. This is an example of a medical inhaler. And apart from sprays, we have many natural applications which involve clouds. Clouds are nothing but it's a group of droplets, okay. And the initiation of rain, okay, it depends, it's basically a multi-phase flow process. It depends on complex interaction of the particles with themselves as well as with the surrounding airflow, okay. And this is another application which is quite relevant nowadays, that is the transport of droplets ejected from common respiratory actions, for example, coughing and sneezing, okay. So, the one of the main concern here, or what one would like to predict here, is that in such scenarios, how far the droplets can be transported, or they can travel, okay, before they settle down or they evaporate. So, this is very important to prescribe the safety measures. Then we have also oceanic sprays. So, where the waves disintegrate into small droplets, as you can see here. So, this is an example where the separated flow and dispersed flow coexist together. So, I gave you an example of ponds, the air flow on a water body like in ponds. So, there this phenomena is less likely, but if you consider the sea in rough conditions, then it is possible that the waves break and generate droplets, okay. And this example is also interesting, that is soap bubbles in air. So, this does not come under the category of the gaseous particles in liquid. So, here basically each bubble, by each bubble we have basically, what do we mean here, the soap bubble. Here we have a thin film which traps some air inside it, but the air behaves differently, the trapped air behaves differently than the surrounding air, because that air itself behaves like a particles, because it has to be transported along with the soap bubble. So, this is a very interesting scenario we have, okay. Then we will move on to the next category, that is gaseous particles and in liquid flows. So, As we have already discussed, so bubbly flows are common examples in this category. So, here in this example you can see how the bubble size and their number can be modified depending on the air injection rate. So, in this case you have basically a column of liquid and you introduce air or any gas, okay, from bottom, and that is how the bubbles are generated. This has several applications, mainly in chemical industries, okay, where we want to enhance the energy transfer and mass transfer between the two phases. The other example is cavitation. So, what is cavitation? So, cavitation is a phenomena where locally the pressure reduces below the saturation vapor pressure, okay, and that is how the phase change takes place, and we have generation of bubbles, okay. And cavitation is a main concern in many applications, for example, in pumps and in fuel injectors, especially in diesel engines where we tend to inject the liquid at very high velocity. The other examples are steel making process. So, here an inert gas is introduced into the molten metal. So, here the objective is to separate the impurities which are usually taken out from top of the molten metal in the form of the slag. So, in this case also these bubbles are very important. The other interesting example is drag reduction using bubbly flows. So, this is known as, there is a typical name for this kind of penguins, okay. So, which generate micro bubbles to reduce the drag such that they can swim easily in the sea. And it is well known that the generation of micro bubbles reduce drag, and this is used in ships for the drag reduction. And also combination of micro bubbles with ultrasounds in blood flows are used for tumor treatment. Now we will look at solid particles in gaseous flows. So, one example is cyclone separator, as you can see here. So, as the name implies, it creates a cyclone or say a swirling flow. So, here the objective is to separate the particles from the carrier phase, that is typically the airflow. For example, in spray dryer. So, in spray dryer you spray into hot air, okay. So, the particles, the droplets dry up, they form particles, but the particles are present in the air. So, you need to separate them, and these are very small particles. So, how do you separate the particles? So, they use cyclone separator, for example. So, in this case the large particles are centrifuged out, okay, as you can see, and they are collected at the bottom while the gas can escape from the top. This is the idea. And the solid gas flows are also used in fluidized bed reactors. So, this itself finds a lot of applications. One application is coal combustion. Okay. So, coal particles are kept in this bed, and then air is introduced. So, at certain air flow rate or velocity, you realize a bubbling bed. So, why this is done? This is again to enhance the interaction between the dispersed phase and the carrier phase. Okay. However, if the gas flow is too high, then the particles will be simply transported pneumatically, which we do not want. The other examples are sandstorms, then solid propellant rockets, and as I have already mentioned, coal-fired burners. So, there are in small scale burners, they do not use fluidized beds, So they introduce the particles along with the flow, along with the air, and the air carrying the particles, they are injected in the form of a jet which undergoes combustion. Then we have dry powder inhalers, we are familiar with that. And also the other natural example is the dispersion of ashes which comes out from volcanic eruptions. Okay. Then we have solid liquid flows. So solid particles in liquid flows. So here is an example of transport of coal particles in using water. Okay. So one interesting behavior, you can see how the particles are, so as it passes through this bent tube, the particles are centrifuged out and they are collected in the peripheral regions of the flow. And this is also used in transport of ores, muddy flows, and another practical application is this nanofuels. So what is meant by nanofuels is that here in this case we add nanometallic particles, we stabilize nanometallic particles in a fuel. The objective is that in that case the volumetric energy release rate will be higher, because the metallic particles can also burn to release energy. So basically you use the same volume of the fuel, but you get higher energy release. So where are the applications? Mainly in defense usually. So then we have another natural application is sedimentation in rivers. So rivers, they basically carry the sediments. So they deposit the sediment at different places. So this is also of interest. And then one can ask, how about the blood flow? So we know that actually blood is not a single phase flow. So it has the liquid phase, which is known as the plasma, and it contains some particles also, which are red blood cells, white blood cells, and platelets. Okay. However, usually this does not come under solid liquid type of flows, mainly because these are not strictly as such solid particles, because they can deform, and also they are biologically active. Okay. So then we have liquid flows, as I mentioned earlier. Emulsions. So here emulsions refer to a colloidal system of mixture of two or more immiscible liquids. Okay. So we basically stabilize this mixture some way. Why I am saying stabilize? So let us say you put oil in water. So obviously due to the density difference, they will be separated. But if we agitate it and use some surfactant, and we break the, let us say, the oil particles into very small droplets, okay, then it is possible to stabilize the oil particles in water, for example. Okay, and this is known as emulsion. The emulsions have wide range of applications, mainly in chemical, food, and pharmaceutical industries. So as you can see here, different possibilities are there. Oil in water, water in oil. We can have even more complex scenario, oil in water in oil. Okay. Similarly, water in oil in water. Okay. And one practical example is water in diesel emulsions, which are used for pollution control. So here the idea is that in case of diesel engines, if we inject this kind of emulsion fuel, and the diesel only, but it carries small water particles, then when these particles burn, when these droplets burn, they release these the water also, so water gets evaporated and it absorbs the heat. So it reduces the heat such that the temperature goes down, and so the NOx level can be controlled. Okay. But here if you see this case, so here we have diesel droplets in the combustion chamber, and here we have the emulsion droplets in the combustion chamber. Okay. So as far as the dispersed multiphase flow is concerned, that does not make much difference. So the difference will be in terms of the properties of the two fuels, but still in both cases we have particles. Okay, in one case you have diesel, in other case you don't have diesel, you have something else, and we need to understand the transport, the behavior of those particles. But this kind of liquids can have their own physics associated with them. For example, while a diesel droplet, if you burn, its size will constantly reduce with or monotonically reduce with time as the droplet evaporates. But in case of emulsion droplets, that may not happen, because you have water inside it, it undergoes vigorous oscillations. Okay, so you will see large change in diameters and fluctuation in the diameter, and also it may undergo something called secondary atomization. It will just be scattered into small droplets. So those things exist. Okay.